So a transformation of functions happens when you put a multiplication factor either in front of the function or inside of the operator in order to modify the effectiveness of the x value within the function, or to modify the effectiveness of the function's output when you graph it. So what that looks like is expansions and compressions either horizontally or vertically of the basic pattern. So where translations were simply moving the thing around, a transformation actually dilates or compresses the function and changes its shape. That's what this sort of Latin means. Trans is to move across, and formations is shapes. So you're moving across the shapes. So it will actually be a change in shape. All right, so the first translation or transformation we're going to do is a vertical stretch, and I'm going to use a logarithm to show you that one. So I need my basic pattern for log. So you're going to have to think about those x values that work really well for log. So the first one is at 0, there is a vertical asymptote. And then the x values that are really nice will be 0.1, 1, and then 10. So the log of 0.1 is -1, and the log of 1 is 0, and the log of 10 is 1. You can check those with your calculator. So what I've got in these charts here then are some x values, and then I have the log of those x values. And the function that we're going to try and sketch is g of x is 3 log x. Now you notice it isn't log x plus 3, it's 3 times log x. So when you see a number multiplying in front, it is affecting the function vertically, because you're taking the output of the function and then increasing it. So when you see a number out here that is a whole number, or a number greater than 1, let me note that down. This is your a value, right? The a value out there in front is what determines the vertical stretch or compression. This particular one has an a value that is greater than 1. So if you see a number out here like 2 or 5 or 7/3, anything that is bigger than 1, you end up with a vertical stretch. Which means it's going to get taller than it normally would be if it's above the axis. The thing you also have to remember, though, is that anything below the axis goes deeper. So it's taller / deeper. All right. So if I were to fetch myself a grid and get my axis on there, the basic log function, which I have over here, has a vertical asymptote at 0. When x is 0.1, log is at -1. When x is 1, log is 0. And when x is 10, log of 10 is 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1. Now, I could sketch that in. I'm going to do the transformation first so that I don't get lines all over the place on my grid. So mathematically, the way you do this these numbers are log x. What I'm trying to sketch is 3 log x. So all I have to do is take these numbers and triple them. So -1 times 3 would be -3. 0 times 3 would be 0, and 1 times 3 is 3. And a vertical asymptote which goes to -infinity will be -infinity times 3, which is just -infinity. So what I've got here then is this dot, this one right here, that used to be at 0.1 -1 will be at 0.1 -3. And you see that's this thing. This dot was under the axis, so it is forced deeper. It is forced further away from the axis than it already was. This dot was right on the axis, so it doesn't matter. You stay right there. If you're 0 away and you make that 3 times farther, you're still 0 away. This dot was up 1, so if I triple that, make it 3 times further away, then it's up here. It is 3 times taller than it used to be. So now that I've got these dots still lining up in a logarithm pattern, I just need to color them in. So if you can see the original log passing through here, maybe I'll just dot it in for you. Do you notice that on this side of the intercept, that the pink line, the transformed logarithm, is deeper than the original was? And on this side of the intercept, the transformed function is taller than the original was, as predicted up here. For the next example, I'm going to use the base function 3 to the exponent x. So I'm going to have to make my table of basic values. So for an exponential, we usually use -1. That's a 2. -2, -1, 0, 1, and 2. And I'm not going to bother with 3 because 3 cubed would be 27, which is way off my grid. Well, what the heck? Let's put it in. So 3 to the -2 would be 1 over 3 squared. That's 1/9. 3 to the -1 would be 1 over 3. 3 to the 0 is 1, because anything to the exponent 0 is 1. 3 to the power 1 is 3. 3 squared is 9, and 3 cubed, as previously advertised, is 27. So that's 3 to the exponent x. So the function I'm going to try and transform then will be g of x is 1/2 of 3 to the exponent x. So I look at this number here and I notice that it is outside of the function and it's a multiplication factor. That makes it an a value. And this number here happens to be less than 1. So I have an a that is still a positive number but is less than 1. That means that it will be a vertical compression. Which means that when I'm done sketching this thing, the function should be shorter. Anything above the axis will be closer to the axis than it used to be, or shallower. Anything that was under the axis will be drawn up closer to it. So if I were to fetch my axis, get my untranslated axis on there. At -2, I used to be at I used to be at 1/9. At -1, I used to be at 1/3. At 0, I used to be at 1. At 1, I used to be at 3, 2, and 9, 3, 4, 5, 6, 7, 8, 9, and 3 and 27, which is way off my grid. So these dots, after I apply this transformation, should be getting shorter or shallower. So I should expect this function to be squashed closer to the axis. So how much am I squashing it by? Well, these are the values of 3 to the exponent x, and I only want half that. So half of 1/9 is 1/18. Half of a third is a sixth. Half of 1 is a half. Half of 3 is 1.5. Half of 9 is 4.5. And half of 27 is 13.5. So when x is -2, instead of a 9th, I'm at an 18th. I can't really tell the difference over here. Instead of a third, I'm at a 6th. Again, it's hard to tell. Instead of 1, I'm at half. Instead of 3, I'm at 1.5. This is where I start to see the difference in the behavior. At 2, I'm at 4.5. So 1, 2, 3, 4.5. It's about there. And when x is 3, I'm at 13.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13.5. So if I sketch that in, I still have this horizontal asymptote here. And my exponential takes off like so. This thing used to have a horizontal asymptote and then take off like this. And then by the time I got to this grid point, I was way off. So you notice that the transformed function is shorter or closer to the axis than the untransformed version was. For the third example, I'm going to use a rational function. So I'm going to need to generate my basic pattern for this one. With the rational, we were using -2, -1, 0, 1, and 2. Because all of these numbers end up as fractions anyway, so it doesn't matter which ones you pick. We're going to remember that 1 divided by 0 is infinite or undefined, so there's a vertical asymptote here. And so the function I'm going to sketch then with my transformation is g of x equals -5 over x. Now that doesn't look like a normal a value, so I'm going to factor it out in front. So it would look like this. So if I do that, because -5 times 1 over x would be -5 over x. If I write it this way, I can see that it's a number in front multiplying. It is not inside the function. That makes it an a value. And it is an a value that is less than 0. Now when you have an a value less than 0, I'm getting a reflection. And since it's an a value, it's a reflection this way, right? It affects the vertical direction. So what used to be up is now down, and what used to be down is now up. So I'm going to write the reflection. So vertical reflection. And since this number is greater than 1, just like the positive a values, if it's greater than 1, it's a magnification. So not only will this thing be flipped, but it will be flipped and then all of the dots will be pushed further away from the axis than they normally would be. So I'm going to need a graph here. And plot on my axis. So this one used to be at -1/2. this used to be at -1, this used to be at 1, and this used to be at 1/2. That's 1 over the x value. What I'm trying to sketch is these numbers, 1 over x, but multiplied by -5. So if I do that, -5 times that thing, -5 times -1/2, well, negative times a negative is positive, and 1/2 of 5 is 2.5. 5 times 1 would be 5. This remains an asymptote. 1 times -5 is -5. And -5 times 1/2 would be -2.5. So my dots used to be at -1/2, -1, and then a vertical asymptote this way. And it used to be 1/2 on this side, 1 on this side, and a vertical asymptote on that side. That was the basic pattern, and then you would do this. Now that I've applied this transformation with the vertical reflection, at -2, I should be at 2.5. So this dot got reflected, so it would be up here, and then it was made 5 times further away, landing at 1, 2.5 squares above the axis. This dot, 1 below, was reflected to 1 above, and then made 5 times further away from the axis. So instead of 1, it's 1, 2, 3, 4, 5. This asymptote down here used to head downwards, but then is reflected. So it is heading upwards. This dot used to be 1 above, reflect it, it's 1 below, and then quintuple its distance. Instead of 1, we're 5. 1, 2, 4, 5. This one, reflected, and then quintupled, ends at 2.5. And this vertical asymptote ends up down here instead, giving us a function that looks like this. So just penciling in the original. Notice that the entire thing has been flipped this way. So there's a reflection. What was up is now down, what was down is now up. And these distances have been made taller because of that factor of 5. For the next one, we're going to use Sine X. So the table of useful x values for sine was 0, pi over 2, pi, 3 pi over 2, and 2 pi. And the value for sine x, sine starts at 0, then peaks, then zeros, then troughs, then zeros. So the function that I'm going to sketch for you now is going to be g as a function of x is sine of 2x. So this one is a little different. There is still a multiplication here. It's multiplied by 2, not added, it's multiplied. The difference is we're not in front anymore. Now this multiplication factor is inside of the function. That makes it a k value. And a k value is a horizontal type transformation. Now, this is a bit abstract. If I were to put in pi here, sine would then act on 2 pi, because I'd have to double it before applying the sine. So that means that the value sine would normally return at 2 pi gets dragged back to only pi on the x-axis. If I put in pi over 2 here, then I would get sine of 2 times pi over 2. That would be sine of pi. So whatever sine does at pi gets dragged backwards to happen at pi over 2. That's taking these dots and it's pulling them closer. So when you have a number in here, a k value that's greater than 1, you end up with a horizontal compression. So the function is crushed towards the axis. So squashed towards axis. All right, so get my grid out. Because it's sine, I'm going to do a 6 squares for pi grid. One, 2, 3, 4, 5, 6. So that's pi. 1, 2, 3, 4, 5, 6. So that's 2 pi. 1, 2, 3, 4, 5, 6. That's negative pi. 1, 2, 3, 4, 5, 6. That's negative 2 pi. And because I've used 6 squares for pi, which is almost 3, I need to use 6 squares for 3 on this side. 1, 2, 3, 4, 5, 6. Means that that's 2, that's 1, that's negative 1, negative 2, negative 3. Alright, so my dots normally would have been 0 at 0, 1 at half of pi, so if that's pi, then half of pi is here, right, halfway. So I get to pi, I'm at 0, 3 pi over 2, I'm at negative 1, and 2 pi, I'm at 0. And then this pattern continues that way, 0, trough, 0, peak, 0, trough, 0, peak, 0. Now, before I sketch this curve in, I'm going to apply this horizontal compression. So compressing by a factor of 2 means that your x values are twice as effective, so they show up in half the time. Let that one roll around in your brain a bit. So if it takes you an hour to get to school at 50 kilometers an hour, if you double the effectiveness of your car to 100 kilometers an hour, then it takes you half the time to get there. That's what we're doing here. So this dot started right there, no problem. This one used to take a full pi over 2 to get there, but now it's twice as fast, so it takes half the time. So instead of showing up at pi over 2, it now shows up at pi over 4. Or if you prefer counting squares, it used to be 1, 2, 3 squares over, so now it only takes 1.5. This dot used to take pi to get there. Now it does it twice as fast, which only requires pi over 2 to get it done. So instead of 1, 2, 3, 4, 5, 6 squares over, I'm only 1, 2, 3 squares over. This one used to take 9 squares, so now it only takes 4.5. This used to take 12 squares, so now it only takes 6. And I've completed one full cycle of my sine, so I can just continue that. I'm going 1.5 there, 1.5 there, and 1.5 there, 1.5 there. On this side, because k values, just like a values, drag both sides of the function in, I have to do this same squashing. So this one was 1, 2, 3, 4, 5, 6, 7, 8, 9 squares over. It gets there in half the time, so it only takes 1, 2, 3, 4 and a half squares to do it. This one took 6 normally, only 3, therefore under 3 under the compression. This was 3, so only 1.5 under the compression. This was 12, so only 6 under the compression, and I can continue the pattern. So I end up with a sine function that looks something like this. Now I'm just going to pencil in what the old one looked like. It used to do this. So you see how this wave has been crushed into half the space? Another way of seeing this is that in the time it used to take 1 full cycle to happen, I have 2 full cycles. Because that's a 2. What I've ended up doing in this function, if you think about it in waves, or if you've taken physics, what I've done is I've increased the frequency of these waves, right? They're happening faster. This number in here, in a wave, defines the frequency of that wave. So my compression here has squashed them so that they're closer to the axis. So the next one will be a parabola. So I need to generate my basic pattern for that. Basic pattern for parabolas. Just use -3, -2, -1, 0, 1, 2, and 3. And then -3 squared is 9, -2 squared is 4, 1, 0, 1, 4, 9. So the function that I'm going to sketch with the transformation is g as a function of x equals 1/3 of x squared. Now, do you notice that there is a multiplication factor in this one inside of the square? So if you have a multiplication factor inside the function, it is a k value. And in this particular case, I have a k value that is greater than 0 but less than 1. So the way to interpret that is that your x values, before I get to square them, I have to cut them in 3. So I've already limited their effectiveness, which means I have to go further out the axis in order to get the same punch from my function. So this one here, this -3, if I pop a -3 in here, the first thing I have to do is divide it by 3, and I get -1. So this value, right, my 1 up on the axis, isn't going to happen until this x value. So I'm taking those values, those dots, and I'm pushing them out from the axis. So if I have a k value that looks like that, this will be a horizontal stretch. And for a k value of 1/3, it means that they will be 3 times farther from the axis. So I'm going to grab my grid then. Put on my untranslated axis. Now my basic pattern for a parabola is 0, 1 and 1, 2 and 4, 3 and 9, 4, 5, 6, 7, 8, 9. This horizontal stretch is saying that I have to take these dots, and however far they are from the y-axis, I have to make them thrice that because it's a third. So this dot is right on the y-axis. It doesn't go anywhere. These ones are both 1 square away. If you're 1 square away and I triple it, then you should be 3 squares away. So 1, 2, 3. 1, 2, 3. These two dots are 2 squares away from the y-axis, so triple that would give me 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. These dots are 3 away. Triple 3, you get 9. So 3, 4, 5, 4, 5, 6, 7, 8, 9. 3, 4, 5, 6, 7, 8, 9. So I end up with this parabola that's been dilated outwards, right? Pushed away from the y-axis. So if I sketch those in there, it looks like this. So applying a transformation to a square root function, we're going to need to have my basic pattern. And for square root functions, we didn't bother using any x values except the ones that had nice square roots, which means no negatives are allowed. I start at 0. 1 is a perfect square, so is 4, 9, 16, 25, etc. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2, 3, 4, 5. So the function that I'm going to sketch then is the square root of 3x negative 3x. Now, you notice that that is a multiplication factor, and that multiplication factor is inside of the function. That makes it a k value. And a negative in either an a value or a k value ends up being a reflection. And so since it's a k type transformation, this will be a horizontal reflection. And because this k value is a number bigger than 1, I'm going to end up with my x values being more effective than they normally would be. That's going to pull the function closer to the y-axis. So it's going to end up being a horizontal compression. Reflection and compression. So if I get my axis out here, you're probably getting tired of hearing me say that. My untransformed function used to be at 0, 0, 1 and 1, 4 and 2, 9, 4, 5, 6, 7, 8, 9 and 3, 16 and 4, but I've lost those dots. So, here we go. This dot here is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares away from the y-axis. Two things happen because of this k value. First, it gets reflected so that it's 1, 2, 3, 4, 5, 6, 7, 8, 9 squares on the left instead of the right. So I've reflected it. Now that 3 says I should get there 3 times as fast, which means it should take a third as long. A third of 9 is only 3 squares. So I'm there. This dot was reflected and then crushed. This one, reflected, would be 4 squares over. A third of 4 is 1.3. That's here. This dot was reflected. A third of 1 is a third. And this guy gets to stay right where he is. Now, I maybe have some room for more of these dots. There was one at 16 over here. So if I reflect it, it's 16 on that side. And then 16, a third of 16 is only 5.33. So I'd be at 1, 2, 3, 4, 5, and a third. This one used to be 25 squares that way. So reflect it, it's 25 squares this way. A third of 25 is 8.3. So 1, 2, 3, 4, 5, 6, 7, 8.3. And I get this lovely square root function happening on this side of the axis. Now notice, negative x's are allowed in this one. And that's weird. You're not supposed to be able to take a square root of a negative. But look at what happens in this function. So you pick negative 4. It's right there. Negative 4 goes in here. Negative 4 times negative 3 is positive 12. And that I can square root. So the positive 12 square root of that is somewhere between 3 and 4. So notice that my function is somewhere between 3 and 4. So the next function we're going to do is going to be a cosine. So I need my basic pattern. X values that we used for cosines were 0, pi over 2, pi, 3 pi over 2, and 2 pi. The value of cosine at those, cosine is at its peak, then zeros, then troughs, then zeros, then peaks. And the function that we're going to try and sketch here is g of x equals minus 2 cosine of 3x. Now, this is a bit of a beast. You notice that there is a multiplication factor in front and a multiplication factor inside. That means that it has had some sort of vertical transformation done to it, as well as a horizontal transformation done to it. So, what do I have here? Well, in front, I have an a value of negative 2. Now, negative means it's a reflection. And a number greater than 1 out in front as an A-type transformation makes it deeper or taller, deeper and taller than it normally would be. That's a stretch. In here, I have a multiplication factor inside of the function. That is a k value of 3. So that's going to make my x values 3 times more effective, which is going to end up drawing the dots closer to the y-axis, which makes it a horizontal compression. And then this was a vertical stretch. So when I'm done, I should have the normal cosine wave, and it should be squished this way and stretched that way. Fetch the axis. You can see it's getting tired. Aren't we all? So I'm going to use 6 squares for pi. 1, 2, 3, 4, 5, 6. That's pi 2, 3, 4, 5, that's 2 pi. 2, 3, 4, 5, 6 is negative pi. 1, 2, 3, 4, 6 is negative 2 pi. And on a 6 squares for pi grid, then I need 6 squares for 3. It makes this 2, 1, minus 1, minus 2, minus 3, etc. All right, here we go. So that cosine pattern used to be, or the basic pattern is peak, 0, drop, 0, peak. And then the same on the other side. Now I'm going to pick on these dots one by one, and we're going to see what happens to them. This one here is 0 left and right, so it is going to be unaffected by this k-type transformation. It is, however, 1 square up from the y-axis. I have to make that twice as far and reflect it. So reflect it and then double the distance. This dot is now here. This dot is on the x-axis, so it will not be affected by this particular transformation, but it will be affected by this one. So instead of being 3 squares out, it has to happen 3 times faster, taking only 1 square to get it done. So this dot is now here. This poor one is not on the x-axis and not on the y-axis, so it is going to be affected by both of these transformations. It's 6 squares out. If that happens 3 times faster, it would only be 2 squares out. Then I have to take it and reflect it to here, and then double the height to there. So that dot is now up there. Having fun yet? This one is 1, 2, 3, 4, 5, 6, 7, 8, 9 squares out. It is right on the axis, so it is not affected by this transformation, but it is affected by this one. If it took 9 and it has to get there 3 times faster, that leaves it only 3 squares to get it done. This dot is affected by both. It was 12 squares. Make it 3 times faster, takes only 4 squares. Reflect it and double the distance. So I now have a full cycle of that cosine. I'm going to get my yellow here. It's that this thing used to be 12 squares long. I could have just drawn a box there that's a third of that width, so it's only a quarter of that width. It used to be 1 unit high, now it's 2, so I'm just going to pencil that in like this. Now I'm going to take that box and I'm going to copy and paste it like over on this side. So notice that it's 1, 2, 3, 4 squares wide and 8 squares high. So 4 squares high. There we go. This pattern, bottom, middle, top, middle, bottom, has to be repeated inside of that square. So bottom, middle, top, middle, bottom. And then it has to be repeated again in the next 4 by 8 box. And then again this way. And this way. And this way. Until I have this function filling up the entire grid. So bottom, middle, top, middle, bottom, middle, top, middle, bottom, middle, top, middle, end up with a curve that looks like this. Etc. So these two transformations have worked in concert. I can see that my basic cosine curve, which is happening here, has been flipped, stretched, so it's twice as high and twice as deep as it used to be, and it has been crushed to take up only a third of the width that it normally would. And again, noticing between 0 and 2 pi, I have 1, 2, 3 full cycles, because that's a 3. For the last example, I'm going to use base 2 exponential as my basic function. I'm going to generate the pattern there. We have typically used x values of -2, -1, 0, 1, 2, 3, and maybe 4. Those are your x's. 2 to the exponent -2 is 1 over 4. 2 to the exponent -1 is 1 over 2. Anything to the exponent 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. 2 to the 4 is 16. And the function that I'm going to try and sketch for you is g of x equals -1/4 2 to the -1/3 x. Now you notice that there's a multiplication factor out front, which is negative, and a multiplication factor inside the function, which is also negative. So I have both a and k values here. I have an a value of -1/4. Now that is a reflection. This is a vertical reflection. And when an a value is less than 1, it takes all of your values and drags them closer to the x-axis. So that's a compression. I have a k value of -1/3. And the negative means that it is a reflection, so I have a horizontal and a k value of that's less than 1 makes your x values less effective, which means you have to go further out in the x in order to get the same punch. So that takes all of your dots and blows them out, or dilates them away from the y-axis. So horizontal reflection and dilation. Or stretch, whichever word you prefer to use. So, for the last time in this video, summon the axis. Draw on my untranslated axis. And I'm going to map my basic pattern on there. -2 1/4, -1 1/2, 0 and 1, 1 and 2, 2 and 4, 3 and 4, 5, 6, 7, 8, and 4 and 16. So we're going to do these dots one at a time. Start with this one, just because it's up and in the way. So this dot, first off, I have to reflect it in A. That would put it here. Then I have to reflect it in K, which would put it here. Then I have to make it 1/4 of what its normal height was. It used to be 8, so now it's only 2. and it needs to be blown 3 times further away from the axis than it used to be. So it is currently 3, so now it will be at 9. So, reflected vertically, reflected horizontally, made a quarter as tall and thrice as far. Check. Now we need to do this one. This is at 2 and 4. Reflect it, a quarter of its normal height, and thrice as far. So instead of 2, I should be at 6. Check. This one, over 1 up 2. Reflect it, a quarter of its normal height, and 3 times as far as it used to be. This one, reflect it, half its height, or quarter of its height, sorry, and a third as far as it used to be. This one, reflect it, half, a quarter of its normal height, and 3 times as far as it used to be. I keep saying half, I have halves on the brain, sorry. Do you notice I've got this feature happening here? My horizontal asymptote, which used to be on the left side above the axis, is now on the right side and below the axis because it got flipped twice. So if I sketch this in, my horizontal asymptote is over here. You get a function that looks like that. An exponential that is not only upside down, but also backwards.